The National Security Science Podcast is a spin-off of National Security Science magazine at Los Alamos National Laboratory. We bring you stories that show how innovative science and engineering are the key to keeping America safe, or, as we like to say, better science equals better security.
Many of the scientists involved in the tests worked far more hours than was expected of them, napping for only short periods of time when they felt they could work no longer without sleep. Some, such as group leader Tom Boyd, catnapped occasionally in their truck-mounted campers which they shared with other scientists. Others napped on the floors of offices and other rooms not being used, said Boyd. I can see two reasons why these men are working such long hours. One is that they've developed an expertise. They are competent in their fields and they want to exercise this competency. The other is that we've been working for this day for more than 10 years, and they want to be here. It's the proof of the pudding.
What had scientists so excited that they slept on office floors? The excerpt you just heard is from the 1972 summer issue of The Atom magazine. For these Los Alamos Scientific Laboratory scientists in June of 1972, the answer for camping at work was awaiting the newly designed and constructed half-mile-long linear accelerator reaching an energy of 800 megavolts, which at that time made it the most powerful accelerator in the world. This article, which you can find a link to in today's show notes, shows pictures of scientists celebrating the scientific success of the linear accelerator with champagne, laughter, and a 30-foot tall banner hung from a canyon wall that read 800 MeV. This June, we celebrate the 50th anniversary of this accelerator facility, today called the Los Alamos Neutron Science Center, or LANSCE. For today's podcast, National Security Science writer Jill Gibson interviews Los Alamos scientist Ana Yobet Mejias, who has spent a significant part of her career using the facilities at LANSCE to do cutting-edge science. Next, we tour some of these facilities with LANSCE director Michael Ferlanetto. And lastly, we dive into history to listen to an excerpt from an article published in 1983 by Louis Rosen, who is known as the father of LANSCE. I'm your host, Brenda Fleming, so without further ado, let's celebrate LANSCE.
First opened in 1972, LANSCE brings scientists from all over the world to Los Alamos to conduct experiments. One of those visitors was Ana Yobet Mejias. Ana has now been an R&D scientist at Los Alamos for more than 2 decades. She has spent the majority of that time doing science using the LANSCE facilities, including PRAD, or proton radiography, which uses protons to act as a lens to photograph highly dynamic experiments, such as explosions, and also the Lujan Neutron Scattering Center, which uses neutrons produced by the proton beam. Today, we talk to Ana about her exciting 19 years at LANSCE.
I was a scientist, an instrument scientist in one of the beam lines there. So we were opening it to the world to do experiments there and work with experimenters from all over the world and within the national security enterprise to get the data. And then I started doing proton radiography experiments. So these are shock experiments, dynamic experiments. So for that, we need to discover new materials and develop new materials. And every time we come up with a new material, we need to investigate its properties. And even to come up with new materials, understanding about why materials behave the way they do helps us kind of predict. We are kind of magicians, right? With neutrons, we can look through materials. We can look what is inside. We can do a whole set of investigations from neutron imaging of devices or assemblies or things like that without having to disassemble them. But from the proton radiography standpoint, then we can look at how these materials behaves under explosive conditions, under pulse power. Our national security enterprise needs to be resilient to a variety of harsh environments. And if we can simulate those harsh environments on site, and we can study and we can compare how these materials behave with what what our simulation says they do, that gives a lot more confidence.
While there are other linear accelerators in the world, Anna says numerous aspects make LANSCE special.
Some other facilities cannot work with special nuclear materials like we can here at LANSCE. Other facilities are not able to do experiments with explosive and special nuclear materials like we can do here at LANSCE. So that's the uniqueness of our enterprise. We are constantly developing diagnostics that are often funded by the national security enterprise that benefit society.
Another benefit of LANSCE is the fact that it introduces new scientists to the lab.
At LANSCE, we have partnered with many universities, and these students very often have then transitioned to staff members at Los Alamos. It's these kind of interactions, scientific interactions, that help us also build a resilient pipeline. More and more students that know what we do, value our mission, and choose to want to stay at Los Alamos after they are done with their degrees.
Anna says the Los Alamos facility is not getting older, it's getting better. She says she admires the scientists who started this project 50 years ago.
How ingenious were those who designed the accelerator. They designed this accelerator to grow. They designed this accelerator to have plenty of possibilities. Yes, lots more experiments. We can couple diagnostics. And because we are an accelerator facility within a national lab, we can do experiments that cannot be done anywhere else, like classified experiments. I think the LANSCE still has a lot to offer. And I think that I am very excited about the future in front of us. I think that there is a lot of opportunity, and that's what I'm hoping to see in the upcoming years.
Anna couldn't be more spot on about LANSCE having so much to offer. For the next part of this podcast, let's go tour LANSCE. Today, we give you a glimpse of LANSCE by visiting the isotope production facility, the Lujan Neutron Scattering Center, and PRAD, or Proton Radiography. With us today is LANSCE Director Michael Furlanetto.
As you may recall, an accelerator is something that takes about a third of the power that goes into Los Alamos County and turns it into radio waves, and then we surf the radio waves to speed up particles to high velocities, and we use the particles to make data, essentially. And so in this case, we are taking essentially protons, using the protons to either do things, so we use them to make isotopes, or we use them to make images of explosions in proton radiography, or we use the protons to make neutrons.
This proton beam supports the 5 state-of-the-art facilities at LANSCE, and today we will visit 3 of them.
So what we'll do today is we'll start with isotope production, where we take our low-energy, relatively low-energy protons, so they're only about 15% of the speed of light, and we use them to turn one element into another.
We head over to the isotope production facility. The Isotope Production Facility, or IPF, produces isotopes for applications in the fields of medicine, fundamental nuclear physics, national security, environmental science, and industrial applications. Just a word of warning, these are operating facilities. You will hear a lot of background noise from fans, ventilations, and so forth.
This is IPF. So the story beneath us is the beamline. So the accelerated protons come through here at 100 MeV. They go into a water tank, and then they hit a target, and that target they use to turn one element to another. A whole host of elements that we've been working on. DOE has a whole isotope program whose job it is to, it's actually pretty cool. Their job it is to find new isotopes, figure out how to make them, and then get a company to make them better so that we can stop making them as DOE and let private industry actually take the burden. And so they've transitioned a bunch off industry already. We stood back up during the early days of COVID, so April of 2020, to make some of those isotopes because the companies were all shut down. They're actually things we didn't usually make anymore, but because patients still need imaging and patients still need treatment, is that, all right, we can do this in the short term. Right now, we're really focused on longer-term things. We're in a phase now of the early R&D of a new isotope that we're going to try and get to industry. And the one we're excited about is called actinium-225. It's a nucleus that emits a bunch of alpha particles in a row. And an alpha particle is a helium nucleus. It has a lot of energy, but it goes very short distance, like 1 or 2 cells over. And so if you can deliver 4 of them in an area, and it's in the middle of a cancer tumor, it just kills the cancer tumor, and then it decays away.
Michael points out to an explanatory poster that shows 2 scans of a man's body. One shows the man's body riddled with black dots. The other is almost completely clear of the dots.
Poor guy had prostate cancer. So all the black dots you see there are metastatic prostate cancer through his body, except for his kidneys and his bladder. His PSA, the blood test they do for prostate cancer, is supposed to be below 4. His was 2,900. So they gave him 3 treatments of actinium-225 attached to an antibody that searches out prostate cancer cells, and this is what happened. PSA down to 0.25, everything gone. One more treatment, they couldn't even detect this PSA. There was so much gone. So there's a huge promise here. The question is, how do you make it economically? How do you purify it enough to be used as a drug? How do you then attach it to something that's going to go treat people's cancers?
Michael continues to talk about the IPF applications in nuclear physics.
When this isn't being used for the isotope program, there's a little bit of free time, and so we've been able to make things of interest to our weapons work as well. So actually, the one I'm going to give you the example of wasn't a weapons thing, it was an LDRD. They made an isotope called nickel-56. Nickel-56 is the isotope in supernovae that make most of the light. So when the star gets really bright, that's because nickel-56 is decaying. It has about a 6-day half-life, and so they made it here on a Tuesday, the Tuesday before Thanksgiving. I purified it on the Friday and Saturday of Thanksgiving weekend over at CA48, and then shipped it back over here to W&R to do measurements on it the next week, and made the first ever measurements of its nuclear properties. So it's kind of cool that we can do that now. To give you a sense of scale, there's a uranium isotope with a similar half-life, and to get a measurement of its nuclear properties in the 80s, they used an underground nuclear test to provide enough signal. So the fact that we can do this now without having to go set off a nuclear device, sort of an advance in how we do things.
Next, we head over to our second facility of the tour, the Lujan Neutron Scattering Center. Here, scientists can use neutrons to do scientific research in national security, academia, and industry. How do scientists use a proton beam to get neutrons? Neutrons have no charge, unlike a proton with a positive charge. So you can't manipulate them like you can a proton with electric fields and magnets. Thus, they are difficult to isolate. To get the neutrons, scientists slam the high-speed protons into a target and knock out the neutrons from the target. This process is called spallation.
And that's actually a process that's remarkably similar to when you break the beginning of a game of pool. Right? One ball goes in, a bunch of balls come out. Well, you have a nucleus of tungsten that has a bunch of protons and neutrons in it. One proton goes in, about 10 neutrons come out. We'll use those neutrons to do things.
We badge into the facility and climb up some stairs to get a view of a massive room filled with experimental equipment organized like spokes that come from a central, heavily shielded targeted tungsten. These spokes make up the different flight paths coming from the beam's target for different experiments.
We are on a flight path right here. So at the end of this flight path, there is a tube that goes to a shutter made of mercury. And so when the mercury's there, it blocks the neutrons. We pump the mercury out if we want the neutrons to come through. They fly down this flight path. When we go back to the parking lot, you'll see it keeps going out there. Again, where you want to measure it, you just decide how far away you want to be. What you see, this one, and this one are all nuclear physics flight paths. And we'll go in that one in a sec. So they are studying the decay of nuclei because of neutrons, essentially. There's a big argon tank there that's a particle physics experiment that's riding along with us. It's actually pointed at the target, but there's no hole in the wall there. And it is looking for dark matter as part of an LDRD project. Because when we make the neutrons here, we make a ton of subatomic particles. It's possible we make some dark matter, and they have a very sensitive detector looking for it over there. So 3 nuclear physics, particle physics. The 2 next ones are materials science. And then there's actually behind this wall, there's a whole other set on the other side. So all 360 degrees around the target, you get to do experiments.
Next, we head over to PRAD, or the Proton Radiography Facility. Invented at Los Alamos, proton radiography uses high-energy protons to image the details of materials driven by high explosives. The first proton radiography was done in 1997.
So it's our 25th anniversary of PRAD and our 50th anniversary of LANSCE.
Michael goes on to explain to us the basic function of PRAD.
Yeah, so the cameras would sit on a table like this, and this gets wheeled into the beam line there. There's a scintillator, a material that takes when the protons hit it, makes light, and then the light gets bounced off mirrors to the cameras, and the cameras see the image. So essentially anything you can measure a density difference on, PRAD can give you a time sequence of images that you can use to really constrain your models and your codes.
So why use protons instead of X-rays, for example, to take pictures?
Because the proton has charge, we can use magnets to focus it, and so we can take a proton beam, focus it down to a point. As it expands again, we can make it a cylinder again and take it right to the scintillator. Whereas in X-rays, we don't know how to focus. So yeah, in terms of things that PRAD does better than anyone else, or sort of competitive advantages of PRAD, having as many pulses as you want is great, because there are processes where you want 50 pictures instead of 3, right? And so having the ability to do that is really useful. The ability to focus through thick things to see thin things in great detail. So focus through a pipe of metal that you need to keep the high explosive from destroying your experiment into the high explosive itself is really unique to protons, to charge particles, but only protons have the power to go through things too. Electrons get stopped at the end. And then we really do a lot of fast imaging here. So the fact that you can take pictures every 100 nanoseconds or so, or 200 nanoseconds, can get you some very quick behaviors that are hard to figure out other ways, right? And doing it all in the same experiment is one of the great advantages here, because you have all the pulses you want.
To conclude this podcast, National Security Science writer Weston Phippen reads an excerpt from LAMP, A Dream and a Gamble by Louis Rosen as told to Nancy Sherritt in 1983. LAMP stands for the Los Alamos Meson Physics Facility, which was LANSCE's original name. This article reflects the dreaming up, promoting, and ultimately building this incredible facility. You can find the link to the full article in today's episode notes.
I want to emphasize one thing very strongly. LAMP was a very great technological gamble. There was a good possibility that what we had proposed wouldn't work, were it not for the fact that we were able, partly by design and partly by accident, to assemble here one of the most competent and dedicated groups of people I have ever seen anywhere in the world. The idea would have ended in failure. We had set ourselves a very difficult goal, accelerating a proton beam, actually 2 beams simultaneously, at intensities never before achieved. The intensities are so high that if more than 1% of the beam goes astray, you make the structure along the beam line so radioactive that they can't be maintained or repaired. It's no trick to accelerate charged particles, but accelerating them with such small loss is very tricky indeed. No one can guarantee it could be done, and, in fact, people who really knew the game were betting we would fail. No one had achieved a transmission of 99% through a half-mile-long machine because charged particles repel each other. They don't want to all go in a straight line. They want to separate, to diverge, and then they will interact with the structures. We had to devise, from very first principles, focusing and beam diagnostic techniques to control the stability of the beam. Now it seems so easy. We start a beam at the injector, and a half-mile down it can be 1 millimeter in diameter. 1 millimeter. We had to develop a most basic understanding of beam dynamics to achieve this, and there are some interactions, some couplings between radial and longitudinal oscillations that are hellishly hard to predict, even today. That was the biggest problem, getting the beam out of the machine with such a small loss. Once we solved that problem, we faced another. A main purpose of the beam was to make pions. To do that, you put a target in front of the beam. When the beam interacts with the target, all kinds of particles and radiation breaks loose. The volume around the target becomes so radioactive that human access to the area is forbidden for a very long time. Even with the machine off, the radiation level in the target is tens of thousands of Roentgens per hour. We knew then, and we know even better now, that no matter how perfectly something is made, it is going to break sometime and will have to be fixed. How do you fix it if you can't get to it and work on it? With remote maintenance. Nobody had ever tried to do remote maintenance on systems so delicate and so intricate as the water and vacuum and electrical and magnetic systems in a target cell. The target rotates on bearings to distribute dissipation of the beam power and is exposed to enormous radiation and extreme heat cycling. We didn't know, and there was no way to find out, whether we would start up the machine, run it at a high intensity for a month, 2 months, 3 months, only to have something in the target break. What would happen if we couldn't fix it? We would have to bury it. That was in the cards. But you have to have faith, and you have to have courage. This game is not for the faint of heart. You have to realize that if things go badly, your name is going to be mud, and you may have to go someplace and live out your life without ever seeing your colleagues again. It takes people of extraordinary courage to stake their scientific future, their professional careers, on something that is really very risky. But people do it all the time. They take the gamble and they may lose. But unless you take these gambles, you can never win. I think we have won our gamble.
A special thanks to Ana Yubet Mojias for her great interview, Michael Ferlanetto for such a fabulous tour of LANSCE facilities, Mark Goley for the tour of the Accelerator, and Nina Roloff for organizing the tours. Thank you to LANSCE Communication Specialist Karen Kippen for helping with this podcast and Jim Cruz for providing informative graphics. And thank you for listening to the National Security Science Podcast, stories from the National Security Science Magazine. You can find the full magazine at lanl.gov/magazine. For more great stories from Los Alamos, including several other podcasts, video series, and interactive stories, visit lanl.gov/discover. That's lanl.gov/discover. And remember, better science equals better national security.